Good afternoon, everyone. You all excited to get started?
Yes.
Okay, after a couple of weeks break.
Yes.
So today we are going to cover a very interesting story. It's a math story. It happened over almost 2000 years. In fact, more than 2000 years. It started all the way back in 6th century BC. It only came to a conclusion very recently, only 19 years back in 1995. So we are going to cover it through like multiple episodes in a serial, right? It's like a movie serial in a TV. We'll start in 6th century BC and step by step we move toward the modern times, only as late as just a few years, 19 years back. And do you guys like stories?
Yes.
Especially suspense thrillers? Okay, but this is a mathematical suspense thriller, okay? So, we'll start with probably this part most of you would have heard. How many of you know, so let's go to 6th century BC and 6th century BC, okay? How many of you heard the name of this person called Pythagoras? Everybody heard Pythagoras, right? Excellent. Okay. What do you know about Pythagoras? History?
Pythagoras, he created the Pythagorean theorem.
Pythagorean theorem. Yeah?
He was a mathematician.
Was a mathematician.
Right triangle.
Right triangle Pythagorean theorem. Yeah? Now, Pythagoras actually did a lot. He was most known for Pythagoras theorem, which we'll talk about in a second. But he was one of the first people, at least actually the first people who were documented, who believed that the whole world, the nature is made up of mathematics. And remember we talked about in the very first class, math is the order of nature. And he was one of the first people who believed that, and he actually started many schools. Just like this, he started an academy. He ran many schools, and they outlived him, which means that some of the schools went for hundreds of years even after him. And so he had many disciples who followed his principles, and they are for example, they believed that a lot of things in nature are made of spherical, because they believed the sphere is the most symmetrical thing, and that's why he is the first who started the concept, later carried on by other Greek philosophers, that everything, all the celestial objects, like Earth, Sun, all the planets, they're all made of spherical objects. So they did know that Earth was spherical, not flat, although most people in those days probably believed that it is flat, but apart from those, he also did a lot of contribution to the mathematics of music. How many of you thought that, how many of you go to any music classes or do music? A lot of you, right? How many of you know that there's actually a lot of mathematics behind music?
I know there's a little.
There's a little, in fact, there's a lot of mathematics behind music. And Pythagoras was believed to be the first person who recognized it. In fact, he wrote books about it. Well, he probably said, and other disciples might have written the books. And even today, many musical instruments that we follow today are based on some of the math that Pythagoras started all the way back in the 6th century BC. The notes in music, for example, the octaves and the Cs, right, the middle Cs, all those, he found that to get a specific note, you need to have a specific length of string. And as you change the length of the string, keeping everything else constant, he predicted what kind of notes that he get. And he actually said that the difference between music and noise, right? Music and noise, they're both sounds. What is the difference between music and noise? He said it is math. Music is noise that follows specific math. If you don't follow the math, if you just randomly come with different sounds, you get noise. But if you follow a certain pattern, mathematical pattern, you get music. And so many musical instruments in piano, right? If you see the pictures of the strings behind piano, not the digital piano, because the digital piano just comes out of like a computer chip, but the actual pianos have strings behind them, and those string lengths are based on certain mathematical proportions, and it started all the way back with Pythagoras, and even guitars and any of the instruments that you see, musical instruments follow those mathematical patterns that all start with Pythagoras. Later went through, of course, a lot more other methods to come up with, but he's the first to start that. But the one thing that we remember him most for is Pythagoras theorem. Okay? How many of you, has anybody who did not hear what Pythagoras theorem is? Most of you don't know what Pythagoras theorem is? Okay, we'll talk about it. And some, probably in the school they won't teach you until late middle school or I don't know, high school. But it's actually a very easy concept to understand, and many of you might have heard from your parents or from some class or maybe from reading a book. It's actually very easy to understand, also very interesting and very useful as well. And it's one in geometry. It's said that probably Pythagoras theorem has the most number of proofs. There are different ways to prove them. Some are very intuitive, some are much more complicated, but it is a very interesting philosophy. So what does it do? Okay, so instead of, I like showing you pictures so it will be easier to understand. Okay, what is this?
Right.
Right triangle, right? This is a picture of a right triangle. So even before Pythagoras, even before the classic Greek times, we now find many evidences that some people in Egypt, probably in Babylonia, India and China actually knew about the right triangle and this specific thing that we're going to talk. Now what we call as Pythagoras theorem. They found that if you take a right triangle like this and the longest side, so the thing about right triangle is one of the angles is right angle or 90 degrees, right? And the side that is opposite to that, the longest side is called, it has a name, hypotenuse. So this is called hypotenuse. And the shorter sides are usually called legs. The long leg and a short leg. Okay? They found that something interesting happens. If they take 3 units of the shorter leg and 4 units of the longer leg, they always got 5 units of the hypotenuse. They also found that if you square this number 3 squared, which is equal to 9, square this number 4 squared, which is equal to 16, 9 plus 16 is 25, which is equal to 5 squared. So they found that the sum of the squares of these two legs is equal to sum of the hypotenuse. Now, before the Greeks, before Pythagoras, nobody identified it as a general rule. They found that this particular combination of 3, 4 and 5 worked. And they figured this out because we know from some of the clay tablets that we find archaeologists find and the papyrus, we know that ancient people knew about some specific numbers like 3, 4 and 5. But the brilliance of Pythagoras is that it is not just for 3, 4 or 5, for any right triangle. Okay? For any right triangle, the sum of the squares of these two legs is equal to the square of the hypotenuse. To make sure you don't get confused, right? Particularly those who have not heard before. Okay, let's take this particular one. This is actually measured. This is actually a 6. This is a 6-inch leg. Okay, I don't have a holder here, but I actually cut it to measurement. Okay, this is 8 inches. And it so happened that when I cut this through 6 inches, this is 8 inches, this actually turned out to be 10 inches. Okay, then what I did is got a 6-inch square. Okay, same as the length of this, right? Okay. This square is not the mathematical square like a power, but it is a square shape. What do you think is the area of this square shape is going to be? Pranay?
6.
The length is 6. What do you think is the area of it going to be? Did you learn the area of a square? What is it going to be?
It's going to be the same, like 6 times 6 is
6 times 6 or 6 squared. So I can actually write it. So this is 6 units. This is 8 units. This is 10 units. Right? So this length is also 6. And because it is a square, this length is also 6. Its area is 6 times 6 or 6 squared. Right? Okay, very good. Alright, now I cut another square whose side length is 8 units. Okay, let me turn the side for a second. So this is 8 units. So this side is 8. Being a square, what will be this side?
8.
8. What do you think is going to be the area of the square?
8 squared.
8 squared are equal to 64. Okay? Now I got a third square whose length is 10 units. Same as the hypotenuse. Right? So what is this length going to be?
10.
10. What is this length going to be?
10.
What is going to be the area of the square?
100.
10 squared. Well, now see the magic. The magic is, if we take, what is 8 squared equal to? 6 squared equal to? 30.
Oh, sorry.
6 times 6 is?
36.
36. Okay? So if I draw this right triangle here, this is 6, this is 8, and this is 10, and so this is 36. Area of this is 6. Area of this is 8 squared. What is 8 squared?
64.
64. And area of this is 10 squared, which is equal to
100.
100. Okay. It was a little bit outside, but it's on 100. Well, let's add up. What is 36 plus 64? 100. Magic. 6 squared plus 8 squared equal to 10 squared. That's what Pythagoras found, that for any right triangle, and in fact, they don't even have to be whole numbers. We took 3, 4, 5, 6, 8, 10, but you can also take, if you take half of this, 1.5, 2, and 5, right? 1.5 squared plus 2.5. Took half of it. So 1.5 squared plus 2 squared will be equal to 2.5 squared. So they don't even have to be whole number. If you take any right triangle, okay, the sum of the squares of the two legs will always be equal to the square of the hypotenuse. In other words, the area of the squares formed by the two legs, right, will always be equal to the area of this. One other way to see is if I put it over here, okay, and I can actually, if we cut this to match this size, do I have scissors? Yeah, you have scissors. So let's actually cut it. Okay, if we take this, okay, if we cut this portion that matches here, if we cut perfectly, to match that. I may not be cutting perfectly aligned, but if you do, right, what happens is this will fit here. Okay. Similarly, if I cut it here, this will fit here, and the remaining piece, interestingly, okay, I cut that 36 units into. By the way, you can find the area of each of these pieces easily. So we can prove, okay, this will fit here, right? And the balance that is fit, If I cut that into the middle, that will exactly fill the rest of the gap. Actually, it's not into the middle. I should have cut. I have to make one more cut because let's get this. Let's see how it fit. Now, the gaps are because I did not cut in straight lines, but can you see that? It fit. In fact, we can also mathematically prove it. How can we prove that? If this is 36, this is 64, and this is 100, let's just take this 100, bigger one. This is going to be 10 and this is going to be 10, right? So, if we take, this is 8, right? The 64 square. This is going to be 8 and this is going to be 8. Right? 8 and 8. That means, and let's fill this. How much is this? 10, the whole thing is 10. This side is 8. So this must be?
8.
10 this part?
2.
2, right? So this is also 2, right? Right? This is 8. So this is also 2. Because this 10 minus 2, right? So what do you think is the area, going to be the area of this rectangle?
16.
Right? 8 times 2 is 16. What is the area going to be area of this rectangle?
16.
What is going to be the area of this remaining square?
4.
4. What is 16 plus 16 plus 4?
36.
36. So this is 64. And the area of the remaining ones is 16 plus 16 plus 4. If you add all of that, you get 100, which is same as the 10 by 10 square. That's how the areas of these two squares formed by the two legs is the same as the area of the hypotenuse. And Pythagoras actually proved this almost 2600 years back. And there are actually many other ways to prove. But this is probably the proof I like the most, because it is so intuitive. You don't need to use a lot of math. You just cut the cardboard and you get the proof, right? And using that, he came up with this formula. Now, the question for you is, we know that it worked for 3, 4, 5, right? We also saw that it worked for 6, 8, and 10. Right? If you have 6 and 8 and 10, it worked. How many, and these numbers, in the 3, 4, 5, which form the three sides of a right triangle, are 6, 8, 10. They're called Pythagoras triplets. They're called triplets because they're 3 numbers. They're called Pythagoras triplets because they form the 3 sides of a right triangle, where 3 square plus 4 square equal to 5 square, or 6 square plus 8 square equal to 10 square. The question for you is, how many such Pythagoras triplets do you think are there? Is it just 1, 2?
Infinite.
She says infinite. They're infinitely many Pythagoras triplets. Do you guys agree?
Yes.
Why? What are the other triplets? Yes, Shruti?
We could just double the numbers, like with 6, 8, and 10.
Right. So she saw what we did first time. So if you look at 3, 4, 5, we just multiplied all of them by 2. Doubled all of them, you got 6, 8, 10. You can multiply 3, 4, 5 by 3, you will get 9, 12, and 15. That will also add the sides of the Pythagorean triplets. You can multiply by 4, 5, or any whole number, you will get infinite numbers. Do you think this is the only set? This is one set, right? So by keep multiplying all 3 numbers with any number, right, you will get as many Pythagoras triplets as you want. Do you think this is the only set, or are there any other numbers? Okay, can anybody knows any other example?
12, 16, and 20.
I know, but you're just that is by multiplying this 3, 4, 5 with a different number. My question is, apart from this whole set, which is infinite by itself, see, so you're correct, they're infinite because you can multiply with any number, infinite numbers to get this. Do you think there is any other set there actually is. For example, 5, 12 and 13. Try this. What is 5 squared?
25.
What is 12 squared?
24.
What is the total?
169.
What is that equal to? 13 squared. So 5, 12 and 13 also form the same thing. It is not based on 3, 4, 5, right? Because you can't get this by just multiplying 3, 4, 5 with anything. In fact, you can get a whole different series based on this. If you multiply this with 2, you will get 10, 24 and 26. Or multiply 3, you get 15, 36 and 39 and so on. You get another infinite set, right? In fact, you can keep going. The next set is 7, 24 and 25. You do your own math later. You can write it down and try it home. This, and you can get this will also, this is also Pythagorean triplet. In fact, you can again multiply this with 2, which gives you 14, 48 and 15 and get another infinite set. Now just that, you can keep going. 9, 40 and 41 and you can try, you will get another set. Do you see any pattern? See, what pattern do you see?
The first number of each triplet, as you go on through numbers, they go up by 2.
Right. And so they are all odd numbers. So you can always get a Pythagoras triplet with any odd number. Isn't that interesting? So, and using the series, you can get another whole infinite series by multiplying the all 3 numbers with any other number. In fact, there is a way to tell. You can take any odd number and I can tell what are the other 2 numbers. It's going to take some time to explain, so I'm not going to get there now. Maybe in a different class, maybe one of my junior classes, we can talk more about it. Because I don't remember all of this. I'm using the formula to get this. But that's a little bit of digression. Okay? The point is that you have an infinite number of sets which match this. Yes,
and also in the second number, they're all multiples of 4.
right. Yep. Good observation. And the third one is always again odd number. Right? But I will talk about some other time how to create. But the point is that there are infinite number of such numbers. Right? And to generalize all this, Pythagoras, like probably other mathematicians, came up with a formula. How can we generalize that with some variables? Yes, Steve?
A squared times b squared equals c squared plus.
A squared times b squared?
Oh, sorry, a squared plus.
A squared plus b squared equals c squared. Absolutely, good job. So, we can summarize the Pythagoras theorem, everything that we talked about so far, with one simple equation, which is an algebraic equation. As we discussed last week, or last class, algebra as a concept was introduced much later. But algebraic thinking was already there in this, right? The notation of a squared plus b squared is equal to c squared, or x squared plus y squared equal to z squared. That notation came much later. We talked about who was the first person who wrote a book on that? Al-Khwarizmi. Do you remember? Talked about Al-Khwarizmi and his book, which had a name. Part of it is Al-Jabr, and the word algebra came from that, right? But the thinking behind that started all the way here. So the principle is, you can call it x squared plus y squared equals g squared. Or you can call it a squared plus b equal to c squared. Doesn't matter. You can use any variables. Does everybody understand this? Anybody who does not understand what this means? Sai? You understand, right?
No.
Oh, you did not understand. Did you understand 3 squared plus 4 squared equal to 5 squared?
Yeah.
Did you understand 5 squared plus 12 squared equal to 13 squared?
Yeah.
So what we are saying is that if you take any right triangle, okay, whose sides are x, y and z, okay, x and y are the 2 legs and z is the hypotenuse. What Pythagoras said is that the square of this plus the square of the second leg, the sum of the squares of these two is always equal to the square of the hypotenuse. Do you understand now? That's exactly, we summarize, instead of using 3, 4, 5 or 5, 12, 13, we generalize it by x squared plus y squared equal to z squared. And we know that there are infinite number of triplets which fit into this. Right? We just proved that. Everybody agrees? That is the first part of the story, today's story, okay? Which is by interesting by itself, right? But now, let's fast forward ourselves by 900 years. Okay, so far we are in the 6th century BC. If you kind of take a time machine, you travel back about 2600 years, right? And we learned about Pythagoras. Now, let's take the time machine, not all the way to 2600 years, but move forward by 900 years to 3rd century AD. Do you think I'm right in saying that there is 900 years or is it only 300 years? When you go from 6th century BC to 3rd century AD, is it how many years, how many hundreds of years there, Sai? From 6th century BC to 3rd century AD, is it 300 years?
No.
How many?
900.
900 years.
Yeah.
One way to see it in a line, for example, with this 0th year, the 6th century BC, BC is, it kind of, one way to think it is like a negative number, right? To the left of 0 is negative numbers, to the right of 0 are positive numbers, so this is 3. So that the, how many years between them is really the distance between them. Now if this is negative 6 and this is positive 3, that is 3 minus negative 6. You know how to solve this? Is 3 minus negative 6 3 or 9?
3.
3? You think it is 3? So 3 remains 3. What is negative times negative?
Positive.
Anybody heard that? Negative times negative is positive. So this is 3 plus 6. What is 3 plus 6?
9.
9. Right? So it is 900 years, not 300 years. So the 6th, don't confuse between 6th century and 3rd century, because this is BC, before Christ, and AD is after that. So its difference is 900 years. Okay? So we took the time machine, moved ahead by 900 years to 3rd century AD. Now, so the previous one, in the 6th century BC, if you remember the math timeline that we talked about a few weeks back, right? This is what we call as the Greek, classical Greek period, right? From there to 3rd century AD, what kind of period was it in Europe?
Dark Ages.
3rd century AD? So it's a Roman, classical Roman period. The Romans defeated Greeks around 2nd century BC. Okay? And from that period until about 5th to 6th century AD, Romans ruled most of Europe. And that's called Roman period, classical Roman period. There are many Greek scholars living still at the time, but it is ruled by Romans. Okay? Who are based in Rome, that's why it's called Romans. And the classical language of Greeks, or in fact most of Europeans during Greek classical period is Greek. The language that most Europeans spoke, at least as a secondary language in addition to their local language, was
Latin.
Latin. Okay, so slowly Latin replaced Greek in Europe, because the Romans spoke that and everybody had to learn that language to deal with Romans, right? So what happened? So this is the second episode in our serial. So what happens here in this TV serial? Well, a lot of interesting things happen, but there is one interesting gentleman, okay, whose name is Diophantus. Anyone heard the name Diophantus? You might have mentioned his name in one of the other classes, but we did not speak at class. He was one of the Greek scholars. He was of Greek origin, but he lived in classical Roman times. He actually lived in the city of Alexandria. You guys remember Alexandria?
Yes.
We talked about Alexandria. It's actually in current days Egypt, which is in Africa. But why do you think the name Alexandria came to that city? Any guess? Switch it.
Alexander the Great.
Alexander the Great, who was actually a Greek emperor, well actually a Greek soldier who became a Greek king and later a Greek emperor. He defeated lots of countries around 2nd century BC, 3rd century BC, still during the Greek times, right? And many cities as he defeated, he named them Alexandria after him. Now, some of them got renamed to other things, but Alexandria actually stuck. And Alexandria was one of the greatest cities in those days. You know, we talked about one specific very famous thing in Alexandria. Yes?
It was about like when Archimedes tried to figure out like he figured out
The circumference of the earth?
the sticks and
The circumference of the earth, right?
yeah.
Not Archimedes, someone else. You guys remember Eratosthenes? So we watched the video of
Oh yeah.
his name is Eratosthenes, who was the librarian of one of the greatest libraries in those times, which is based in Alexandria. Yes?
Oh
You're about to say that?
yeah.
So Alexandria had one of the greatest libraries of all the texts from all different, can you concentrate?
Yeah.
From all different parts of the world in Alexandria. Diophantus also lived in the same city, probably slightly after Eratosthenes. And what Diophantus did was, he was also a great scholar. He did actually studied math, science, astronomy, but his greatest passion was math. And he wrote a series of books called Arithmetica. Okay? He wrote a series of books called Arithmetica, summarizing many math principles, but he wrote it more like in today probably you can kind of consider it like a puzzle book. He wrote a lot of unsolved math problems. At that time, he summarized it in a book. It's actually a series of books. So a lot of interesting things about math, a lot of math that is solved by many Greek scholars until that time, including many problems for which there is no solution. They don't know whether it is true or not, but he kind of asked, so that later people can study it and maybe prove it, and maybe solve those problems. Just like the millennium math problem that we're going to talk about next week. So he wrote but lots of problems in many books. Yes, Shri.
But still, like, how do they know if that problem is true?
They don't know. So some problems probably they solved, they know for true because they solved. Because Greeks solved, like Pythagoras theorem, right? They actually solved that problem, that you can find many numbers that fit into this 3 square plus 4 square equal 5 square, x square plus y square equal to 6 square. They knew that. But when some of them, like Diophantus, started asking other questions extending these things to other principles. So when something is known to be true, we call it, in math or science, we call it a theory. When you say a theory or a theorem, it means that we know it to be true. Like Pythagoras theorem, you know it to be true because you can prove it. Before something is proved, mathematicians usually call it with one of two names. They either call it hypothesis, even in science, the same thing we follow in science. If you want to say that like plants generate their own food, okay? Well, if you know for sure, this is a theory. If you don't know yet and you need to prove, it is an hypothesis. Sometimes it's also called conjecture. Conjecture also means that it's kind of a guess, but it's not more than a guess. If somebody said, well, it looks to be true, and I can give example that it is true, but I don't know for sure. I can't prove that it is true, right? So they're called hypothesis or conjecture. So Diophantus showed a lot of theories in that book Arithmetica, but he also came up with many hypotheses or conjectures. And one of them was an interesting one. That is, he wanted to extend Pythagoras theorem. And he asked a question. It's a hypothesis because he did not know whether it's true or not. He said, well, we know that for x square plus y square equal to z square, and we know that there are many numbers like that, right? But do you think there are any whole numbers that made this one x cubed plus y cubed equal to z cubed? Now, how many of you don't know what is a cube? Everybody knows what is a cube? You're not sure? Okay, I'll explain what is a cube. Okay, how many of you heard the word exponents? Everybody heard what is an exponent? So, for example, when we talk about 3 squared, that is 3 times 3. the number 2 is called an exponent or a power of 3. 3 raised to the power of 2, or for short we call 3 squared, or 3, the exponent of 2 is 3 times 3, which is equal to 9, right? A 3 cubed is called 3 raised to the power of 3, or 3 with an exponent of 3. That means that 3 multiplied itself with this 3 times, right? Because this is 3 times 3 times 3, which is equal to 9 times 3 is 27. The thing with this exponent, they grow very fast. Okay? The next one could be what, Sai? 3 raised to what? Could be next one.
3 times
3 raised to 4 will be equal to how much? Or what should I write? 3 multiplied by itself? 4 times, right? Not 3 times 4, but 3 times 3 times 3 times 3. You write this 4 times, right? Which is equal to 81. You can do, keep going. 3 raised to 5 will be equal to 3 times 3 times 3 times 3 times 3, which is equal to 243, right? You can keep going. And you can do it with not just any number. You can do it with 10. 10 squared, 10 cubed, 10 raised to 4, 10 raised to 5. The first two have a special name, square and cube. After that we just call it 10 raised to 4 or 10 to the power of 4. 10 to the power of 5, etc. Okay? So his question is, we know that Pythagoras proved that there are many numbers, many Pythagorean triplets, where x squared plus y squared equal to z squared. Do you think, or can you show any whole numbers that fits x cubed plus y cubed equal to z squared? And he tried and he did not find any of them. So he said probably there are no numbers, but that's not a proof, right? You can try for 10 numbers, 100 numbers, 1,000 numbers, 1,000,000 numbers, or 1,000,000,000 or 1,000,000,000,000 numbers. That is still not a proof, right? Just because you did not find any examples that fit this in the first 1,000,000,000 numbers, that does not mean that the next number is not going to be fitting into this, right? Mathematicians will not take, or scientists or mathematicians will not take an example as a proof, even if you do it for the lots of examples, right? They need a rigorous mathematical step-by-step proof that, oh, just like we showed for Pythagoras theorem, right? It always works. You need to show that it always works and it will never be wrong. But he was not sure. But he asked a question. He left this part here, but he did not completely leave them. He said, okay, I did not find anything for cubes, but do you think you can find anything with a fourth power? X power 4 plus y power 4 equals z power 4. Or x power 5 plus y power 5 equals z power 5. Like a 3 power 5 plus 4 plus 5 equal to 3 power 5 plus 4 power 5 equal to 5 power 5. Well, it is not true, right? He did not find any numbers and he said, okay, I'm going to generalize it further. Okay? For not just for 3, 4 or 5, for any number, for any exponent, do you think you can ever find something that finds? So, well, we're going to put 3, 4 and 5 with a number called n. We're just adding variable, one more variable, okay? He said, do you think you can ever find any equation that satisfies with whole numbers x power n equal to y power n equal to z power n? And he did not find examples for any of these powers. But he was not sure, right? Because math was relatively premature in those days. He could not prove, but did not find any example. Then he asked it for later generations. Can you guys find any examples? Do you think that any numbers, any whole number that fit this? And unfortunately, nothing much happened for the next 1400 years. Because what happened after the 3rd century or about Roman period?
Dark Ages.
Dark Ages started. Well, actually not for another couple of centuries. Probably the Romans were still doing pretty good until 5th or 6th century AD. But after that, Romans were defeated by a number of regional tribes, what are called Germanic tribes in Europe. And Europe kind of became splintered. For the next 700, 800 years, nothing much happened from 5th, 6th century. But as far as the Diophantus book is concerned, not a whole, this particular problem is concerned, not much happened for next 1400 years. Except that starting around 14th from about 14th to 16th century, something happened in Europe. We talked about in one of the previous classes. Do you know what happened around the 14th to 16th century?
The Renaissance?
The Renaissance. So what was Renaissance? The Renaissance was the period, yes, Pranay?
Like it was like when Europe like started like going into math and science and figuring out new things.
Yeah, so they started asking interesting questions. In fact, the way they started, they did not start with math or science. Most of it they started with art actually, or literature. Later it went to math and science. But the thing was, they said, look, Europe had a great history many, over 1,000 years back. They were asking at the time, in 14th, 15th century. Because we had classical Greeks, classical Romans, during which a lot of Greek books and Latin books were written. We had a great art, great music, great literature, great math and great science. But for last probably 700-800 years, nothing much happened. Let us try to find what was the great things that Greeks and Romans did way back, more than 1,000 years back. Their sources were, now what was happening, although we call it dark ages, well it was dark in Europe, but rest of the, we talked about in other classes, right? In Arab world and India and China, a lot of interesting developments were happening. But even within Europe, the biggest thing probably happened from a Roman period until the Renaissance is Christianity spread. Christianity obviously started with Christ in 0 AD, but it started spreading from probably 3rd or 4th century AD and all the way through Renaissance. While Christianity was spreading, they had things called, what they call monasteries. And monasteries were monks or the saints, Christian saints or monks live. They're very pious, very religious. They follow all the Christian principles, but they also taught a lot of religious principles. Along with religious principles, they also taught a few things what they call secular, not related to religion. And they actually preserved some of the books from Greek and Latin times. So these Renaissance scholars who wanted to find the great things that happened during the Greek or Latin classical periods, they dug through and they visited the monasteries and found the books. Most of the books from the Greek time, they were written in the language of Greek. But when the Renaissance came, the main language in Europe was still Latin. Okay? Later down, after the Renaissance, and the concept of countries came up. By the way, at this time, there was still no concept of countries. Today, we take countries for granted. Oh, we are from United States, we are from India, we are from England, we are from Italy. Well, in this period, there really no concept of countries or nations. It was more of kingdoms. There are a lot of kings, right? And although they had some identity based on the language or customs, traditions, etc., there was no country. During Roman period, everything ruled by Roman period is ours, right? It's Roman. There is no Italy or no France or no England at that time. That came much later, mainly during probably 15th to 19th, 20th centuries. If you look at Germany, for example, as a country, formed as late as 19th century, in around 1870, that is when Germany is formed. Until then, it's just a collection of large kingdoms, what they call principalities and kingdoms, etc. They had Prussia, Bavaria, all those were different kingdoms. There were all 300 of them. It's a whole interesting story by itself if you dig into history, right, how the country of Germany got formed, or country of any of the European countries formed, or any India got formed. India was also not one country, although Europe referred to it as India. It was a lot of different kingdoms were there, right? The concept of country or nation is a relatively recent notion. Recent, in the sense, last few hundred years, not a few years, but few hundred years. But in the long history of human history, it's just a few hundred years, right? So, going back to this, during Renaissance, the Latin was the predominant language. So somebody translated Arithmetica from Greek to Latin, which is a good thing. Because now more people can read, because not many people were know Greek by this time, except probably those who are living in Greece itself, because most of it is got replaced by Latin. So now let's fast forward to the third episode of Syria. The third episode so from here to here moved by 900 years. Let's fast forward by another 1400 years. So our time machine gets us to the 17th century AD. Okay? So what was happening? By 17th century AD, in Europe, many countries already started forming. And one such country was France, which is still a country today. Right? Germany was not formed yet, but France was a country at that time. In France, there was a city called Toulouse. And in Toulouse, there lived a gentleman whose name is Pierre Fermat. Anybody heard the name Fermat? It's actually F-E-R-M-A-T, but it's pronounced like Fermat, T silent. The word Fermat? Yeah. So, in fact, we talked about him in the last class. I don't know whether you guys paid attention or not. He was a lawyer by profession. So, he's not a mathematician. So, why are we talking about lawyer here? Not liar, liar. And he was also, and when you, as a lawyer, when he does well, he became a judge. So, at this time in his career, he was more of a judge. But when he does the judge, when he completes the judge work during the day and comes back at home in the evening or the weekends, he has a hobby. Like a lot of us have hobbies, right? Some of you may have hobbies of stamp collection, some of you may have hobbies of doll collection, whatever, right? He had a hobby. His hobby was math. It's a nice hobby to have. Isn't it a nice hobby to have? And I hope when you guys grow up, some of you hopefully might like mathematics and become mathematicians. It's a great career to have. But not everybody becomes a mathematician. But even if you are not a mathematician, you might become, I don't know, a doctor, or a lawyer, or an engineer, or a sociologist, or the president of United States. Whatever you become, I do hope that mathematics is going to be one of your hobbies. Because it's a hobby means because you do it because you like to do it. Just like it's my hobby. And some of you might start an academy like me. Right? If you like it, and you may start teaching. It's a great hobby to have. But Fermat had that great hobby. But it's not just like any hobbyist, he's a very serious hobbyist. He actually solved many new math problems and many unsolved problems. He published many books too. In fact, what we talked about in the last class about him is regarding probability. I don't know whether you guys remember, after Cardano, we talked about two French mathematicians had a series of letters exchanged between them as part of probability to a gambling. Who are those two?
Newton and...
No. Newton and Leibniz were related to calculus. Right? They both kind of what we call co-invented calculus. This is slightly before Newton and Leibniz founded calculus around 1670s to 1680s. We are talking about Fermat lived from around 1601 to actually 1665. So that is the period when he lived. So it's slightly before Newton and Leibniz. But these two, Fermat and another one is called Blaise Pascal. Remember Pascal? Talk about Pascal.
Yeah.
So Pascal and Fermat exchanged a series of letters. In those days there were no emails, right? They were actually physical. They wrote letters to each other. They talked about probability theory. And they are actually one of the pioneers of probability. Still as applied to gambling, of course. Most of the probability theory when it started was applied to gambling. That was the most direct application because you can make money out of gambling. Especially if you know the math behind, because most people did not know the math behind. They blindly guessed in gambling. By knowing the math, they can always beat the others. They can find the probability of what die can come and they can win. Right? Yes?
Fermat and Pascal were the inventors of probability?
They're not the first. Cardano probably is known to be wrote the first book about probability. And but Fermat and Pascal are one of the pioneers. Pioneers are one of the first people to use it scientifically. Later down, but the person who probably first wrote a book on probability as applied to not gambling but general mathematics and what we call the theory of risk management or decision making. And his name is Johannes. No, not Johannes Kepler. Johannes came from the great Swiss family. We talked about the series of mathematicians. Bernoulli. Bernoullis were a series of mathematicians, actually multiple generations of mathematicians. He's the first. But Fermat and Pascal did a lot of original contribution to probability. So the point is that Fermat actually was part of a lot of interesting math, including some parts of calculus, although calculus was formally not invented, but we said that during calculus there are many other mathematicians who kind of touched calculus from different angles, right? Fermat also did some of it. But what he was most remembered was for something very interesting. He found a Latin copy of Arithmetica, okay? And because he loved math, he wanted to find interesting books, and the Arithmetica was a very interesting math book because it had a lot of interesting problems about math, some solved, but many of them are not solved. So it gives future mathematicians opportunities to go and do more research or solve it. And he had the habit of, he took the book, and the margin of the book, if he had any interesting idea, he wrote it, or some problems he actually solved on the margins. And for some problems where the margin was not sufficient, he wrote an interesting comment, which probably kind of irritating for later mathematicians, but also it led to a lot of interesting stories. That habit was, he wrote a note that I got a very interesting proof for this. I actually know how to solve this, but this margin is too small to write my note. And he wrote it for many of them. But having done that, so if you do that and somebody else finds that book, right? What do you think? If you are a mathematician, especially if you say, I know this, how to solve this. This is a very hard problem. Nobody solved it for the last 1,000 years. I know how to solve it, but this margin is too small. And what do you think about it? Everybody is interested, right? Oh, what did you tell me? But here is the problem. The book was not found while Fermat was alive. He died in 1665. Nobody found the book during his lifetime. After he died, I think either his son or his grandson found that book of the copy of the Arithmetica with his father's or grandfather's notes. Said, okay, these are very interesting notes because some of them actually solved. Because many problems which were not solved since Diophantus actually were solved by Fermat. So they wanted other people to know. They published a book. His son or grandson, I think his son, he published a book with all the notes from Fermat, giving credit to Fermat that he actually solved this. But they published as it is with all notes, including his notes that, oh, this problem, I know the proof, but the margin is too small to write the proof. Now, they published the book, now it's out in Europe, so remember, the 17th century is a very fertile ground in Europe. Like a lot of people, scholars were starting to read math and science. Yes, see.
Why did he just use like 2 margins instead of 1?
I don't know. Maybe he wrote it in another notebook that we did not find, that nobody found. We don't know what happened, right? See, if it was found during his lifetime, somebody could have asked, okay, can you show me the proof? Where did you write? But he's dropped dead by the time we found the book. You can't ask him. You can't ask a dead person. So now, if you give this book got published in Europe, a lot of mathematicians looked at it. Some of them got really irritated. Hey, come on! If you really found a solution to such an important problem, why don't you tell us? Right? But they also wanted, because the comment is there, a lot of people tried to solve many of these problems. In fact, over the next few years or few decades, most of the problems for which Fermat said that, look, I had the proof, they actually proved it. Again, one more time, other mathematicians proved it. Except one problem. That was this Diophantus problem of x power n plus y power a equals to z power n. This one proved to be a very, very nagging problem. Oh, where n is greater than 2, right? So where n equal to 2, we know that it's Pythagoras theorem, right? Because then x square plus y square equal to z square, we know that there are many numbers. So Fermat said that I have a proof that there are no such numbers. There are no such numbers. I have actually a very elegant proof. Okay, I have beautiful proof that there are no such numbers. Not guessing and checking that I have proof, a step-by-step proof that it's There can be no such number, even if you go to billions, trillions or zillions, there are no such things. I have proof, but the margin is too small. So, it was such a nagging problem that for over 300 years, nobody could solve it. Some of the brightest mathematicians in the world from mid-1600s to the 20th century tried to solve, including such great scientists as Euler. Remember we talked about Leonard Euler? He made a lot of great mathematical solutions we still use today. He tried, he failed. Carl Gauss was considered as one of the greatest mathematicians ever. He's compared along with Archimedes and Newton, and Carl Gauss as considered one of the greatest, three of the greatest mathematicians. He tried and failed. And Sophie Germain, who is one of the greatest female mathematicians ever, she tried, she couldn't solve. Some of the greatest mathematicians, mathematical mind, over the next 300 years tried solution to this. Nobody could solve. They got even more irritated. Why did you tell us? But some of them solved them for specific ends. Like for example, Euler proved that for x cubed plus y cubed equal to z cubed, there are no solutions for this. Euler did prove this one. Some other mathematicians proved it for n equal to 5 or 6, etc. But nobody could prove for any n you could never have a solution. Okay? For a long, long time. Obviously, if you can't find a solution, everybody wants to find a solution, right? If you're a mathematician, and so this, by 20th century, this is already considered as one of the greatest ever unsolved problems in mathematics. So if you're a great mathematician, solve this and you will be the greatest mathematician ever, right? So everybody wants to find a solution, because if Euler and Carl Gauss and Sophie Germain and all these folks cannot solve, it must be a great problem, right? Everybody wants to solve. But by the time 20th century came, most people believed that you cannot solve this, right? Because every great mathematician of this time considered this and could not solve. Probably it's unsolvable. Now let's fast forward another couple of years, actually about 300 years later, to 1963. Okay? What happened here? We're getting to modern times, closer times. Well, you were still not born, but your grandparents were born probably at the time. There was a 10-year-old boy who lived in Cambridge, England. Now, Cambridge is, any of you heard about Cambridge? It houses one of the greatest universities, even today one of the greatest universities, but it was definitely a great university at the time. What is the name of the university? Cambridge University, right? There's one very famous person, many famous people went there. Do you know any famous people? Newton actually studied and taught there. So there's actually an institution named after him, which we are going to revisit this later in the class today. So there was a 10-year-old boy, probably about the same as some of you, about the same as. He used to like to go to library, and Cambridge has some good libraries. He went to a library and he came across this problem. And by the way, because all other of Fermat's problems were solved, but this is not solved, this was used to be called as Fermat's last theorem. Last theorem because this is the last unsolved one. Right? Everything else that he said, a margin is too small, others have proved. But nobody could solve this one. So that's why I called it Fermat's last theorem. Today, if you want to find about Fermat's last theorem is considered one of the greatest math problems ever. Until recently unsolved, yes.
Oh, it was solved?
Well, wait. There's a suspense. Suspense thriller, remember? We're 1, 2, 3, we're in the 4th episode. 6th century BC, 3rd century AD, 17th century AD, we are 20th century, 19th century. So you have to go a couple of more episodes. I can't tell you the last part of the... See, if you go to a suspense thriller, and I will tell you what is the last page, there's no suspense anymore.
I just want to know if
Right? So 1963, this 10-year-old boy came across this problem. The beauty of this problem is that a 10-year-old can understand what the problem is. Like most of you, all of you understood what the problem is. You don't know how to solve it, but you understood the problem, right? Some of the math problems, gate models, are so abstract it is difficult for a 10-year-old to understand. But this one, the beauty of it is that anyone can understand, because it looks so much like a Pythagoras theorem, much more you can understand. If Pythagoras theorem has an infinite number of solutions, how can you say that there is no solution for any n greater than 2? Right? It doesn't make sense, right? That's why it's so intriguing. That's why everybody wants to solve it. Nobody could solve it. Some of the greatest mathematics could not solve. So, this boy thought the same thing that many of you might be thinking right now. Right? Let me give it a shot. So, he tried, but then he found that his knowledge of math for a 10-year-old probably is not sufficient. And it was in the back of mind, kind of forgot, but it's in the back of mind for a while. Right. Let's now fast forward to another 23 years to 90. So this is the fourth episode, right? This is the 300 plus years. So next one, another 23 years to 1986. Now, oh, by the way, the name of this 10-year-old boy was Andrew Wiles, whom you may not have heard, today is one of the greatest living mathematicians.
He's actually still living.
He's still alive. And he, in 1986, was a professor of mathematics at Princeton University in New Jersey. By the way, Princeton University is one of the great universities in this country. So some of you might, when you grow up, might go there. Now, the other great universities, but Princeton is a great university to go, especially if you want to pursue science, math, engineering-related fields. It's a great university. So he's a professor at mathematics there, which means that if you're a professor of mathematics at Princeton University, you must be pretty smart, right? Even if you study there, you got to be pretty smart. If you're a professor of mathematics there, you must be pretty smart in mathematics. By 1986, is probably in his mid-30s, and this problem kind of his childhood dream to solve this problem, but he kept it on the side. He probably revisited a couple of times. Actually, he was at Cambridge before that as a graduate student, and he worked with the professor, and probably they concluded that it's not solvable. But by 1986, a few other unrelated things are happening in math, because math constantly evolves. Completely unrelated fields are happening, and he thought maybe he can give a shot again. Many people know Andrew Wiles is also an extremely shy person. You know what, shy people, some of you might be shy. You don't really want to talk to others about your feelings or what you want to do, because you're just private, right? Andrew Wiles was one of them. Very low profile. He didn't want publicity. He just does his job. But he had a passion. His childhood dream to solve this Fermat's last theorem. It's unsolved for over 300 years. In fact, unsolved, if you look from Diophantus times, unsolved for almost 2000 years, right? And nobody could solve, but it's considered by 20th century the greatest unsolved math problem ever, right? Yes?
Was it one of the 7?
We'll get there. That's for next week. Okay? We're still in 20th century, not 21st century. Those 7 are for 21st century. Okay? So, he wanted to give it a shot. But he did not want to tell anyone. Because if you tell someone that, look, I'm going to solve the greatest math problem which Carl Gauss and Sophie Germain and Wiles could not solve, but I'll try to solve, people might ridicule. And especially if you're a shy person, you don't want to mention. So he did not mention to anyone. In fact, even his wife really did not know. Probably she had hints that he's doing, and a lot of other professors in Princeton, based on what he's doing, he's doing something interesting, something suspicious, but he's not telling anyone. He's spending a lot of time. He kind of took what is known as sabbatical. Do you know what is sabbatical? No. So if you're a college professor, sometimes you can take a sabbatical to just work on some interesting thing for a period of time. He kind of took a sabbatical for the next 7 years. 7 years of his prime time from 1986 to 1993.
How old is he now?
You can calculate.
50.
You know math, right?
Yeah.
So he was 10-year-old in 1963, and what do you think his age will be now?
70s.
40, 30. 40, yeah, 40.
2014?
Easy.
I mean 1996? 1996 is 33
No,
probably.
1993.
1993 must be 40-year-old, right? He's still alive today. So he must be in 60s?
61.
61. Yeah. So, for these 7 years, he just worked on this one problem. Kept everything else on the, probably was teaching 1 or 2 other classes which are like, he can do it in his sleep, right? But and nobody knew what he was working on, the secret project. For 7 years, he constantly worked using the latest mathematical techniques which were not available to certainly to Fermat, to Carl Gauss or Sophie Germain. They were 20th century developments in mathematics because math evolves in different fields. And some of the fields that he used, actually you will not be able to completely comprehend. So I will not try to explain, even I don't fully comprehend. But I can give you the names because maybe some of you will get interested sometime and try to do some research in future. But keep it in the back of your mind, just like Andrew Wiles was 10-year-old when he had his dream. You don't know what goes to your mind, huh?
I just sound like how old is he now?
Okay, let me just he was 10-year-old in 1963.
So I just did, since he was 10-year-old in 1953, I just,
1963.
yeah, so I went back, 10 years to 1953, and then subtracted by 2014.
So what is it?
61.
61. Okay. So I'll give you some of the names of the principles, the concept that you use a little later. Maybe it will go to your mind, and maybe you want to spend more time in future. But by 1993, by June of 1993, he thought he might have found a solution. Now, he's a very shy person. So he didn't want to go and tell the whole world that, look, I found a solution to Fermat's last theorem yet, because he was not sure. In fact, by this time, almost everybody believed in mathematics around the world that Fermat's last theorem is unprobable, unsolvable. You can use latest computers in the world to find that there are no numbers that match for million, billion, trillion, zillion numbers, but that's not a proof, right? Because you can always go bigger than that. There's no end to infinity. But there are some other completely unrelated fields in mathematics are coming together, which kind of help Andrew Wiles in a direction. And that's one more thing. If you take a really challenging task, right, like solving a Fermat's last theorem, maybe trying to solve some of the 7 problems that we are going to discuss next week in your lifetime, I know it will take several years to even understand the problem. Maybe it will take 23 years to understand the problem. But if you take a challenging task, initially there will be a lot of hurdles. But also, some completely unrelated things will happen positively that will help you. And that happened Andrew Wiles. And what happened was, there's some completely unrelated field that's happened for 20, 30 years before that. In a field, in geometry, very complex geometry, not the triangles and squares that we deal with. They're called elliptical curves, not ellipses. These are 3-dimensional complex curves called elliptical curves. I won't try to explain what they are. You can actually Google research later if you want to. Write down, maybe you want to find more about them later. And there's another thing called modular forms. They're very complex modern mathematical principles. And based on them, 2 Japanese mathematicians, Taniyama and Shimura, and you don't even need to try to remember the names, but you can write down if you want. It's called Taniyama-Shimura conjecture. What does a conjecture mean? I talked about conjecture earlier. What do you think is a conjecture in mathematics or science? Suchin? and a hypothesis, an unproved thing, right? So Taniyama and Shimura proposed that the elliptical curves and modular forms are identical, which they, until that time were proved to be known to be completely different. And Taniyama and Shimura came up with this, what was considered an impossible conjecture, that they're actually same when you interpret mathematically. Don't worry what it means, okay? You can try to understand. But I'm trying to just give you some background and a few names so that maybe someday you want to do some research. Which has nothing to do with Fermat's last theorem, because it's so far away from what we're discussing. But in, I think, late 80s or early 90s, someone, a different mathematician, came up. He actually proved that for some very bizarre mathematical reasons, Fermat's last theorem, if you look at its geometric interpretation, geometrically in three-dimensional space, these are all three-dimensional space, because x square plus y equal to z square is geometrically very simple, it's a right triangle. But when you go to nth power, they become very complex three-dimensional and multi-dimensional geometric figures. Fermat's last theorem, which is so easy to understand mathematically, x power n plus y power n equal to z power n, is actually equivalent to Taniyama-Shimura conjecture, which was completely, nobody anticipated that. But a mathematician actually proved that they're actually equivalent, mathematically equivalent. Okay? What does that mean? Well, both are unproven as of now. Right? Nobody proved Fermat's last theorem, but nobody proved Taniyama-Shimura conjecture either. Taniyama-Shimura just hypothesized. You don't get much when they're both are unproven. But Andrew Wiles thought, if I can somehow prove Taniyama-Shimura conjecture, which was again thought to be impossible to prove at that time, if I can somehow prove this, prove Fermat's last theorem, because they're same. Because somebody already proved that they're actually equivalent to each other, right? So that is how he attacked that problem. And those 7 years he worked very hard by himself, secretly almost, because he's shy. He worked on, and by 1993, he thought he solved this. But he still was not ready to tell the world that he solved Fermat's last theorem, right? Because he's not 100% sure, because it's a very complex proof. He spent 7 years using some of the most, in fact, on the way, he solved many unsolved problems, many other problems. He found some new mathematical concepts altogether to reach that conclusion, right? So, without telling that he solved Fermat's last theorem, he went to Cambridge, because he's very close associated with Cambridge University. He went to actually this institution, which is named after Sir Isaac Newton. It is called Sir Isaac Newton Institute for Mathematical Sciences. It does research in advanced mathematics. He went there, he gave a series of 3 lectures between June 21st to June 23rd in 1993. And he basically called that, he basically explained, without telling what he did, was that he might have found that Taniyama-Shimura conjecture was true. That now, if you're a sharp mathematician, you can conclude that that means that probably you're telling that Fermat's last theorem is proved. But he did not want to tell directly. So, but immediately that was the newspapers around the world, mathematical papers around the world. Like every mathematician immediately got wind that, look, Andrew Wiles seemed to have proved Fermat's last theorem, because he said that he's proved Taniyama-Shimura conjecture, which, by the way, was hundreds of pages of proof. It's not a simple one paragraph proof. So, and using latest mathematical techniques, so most people don't even understand what he was saying, even after giving his. But some of the mathematicians who are working in that field can understand that. So, over the next few days and few weeks and few months, people actually went over, because once you publish, when you give a series or publish something, it is publicly available to everybody. Most people don't understand, so don't bother to look at those papers. But if you're working in that field, if you're a mathematician, you can understand, right? So mathematicians around the world got a complete shock. And this Fermat's last theorem, which is now, by now, definitely the greatest unsolved problem in the history of math. Now, Andrew Wiles might have solved the problem. So every mathematician wanted to review it. And typically, what happens in math and science is when you prove something or when you come up with an invention or discovery, okay, and publish it, others who are working in that field review it. It's called a peer review. Peers means equals, right? Other people who are kind of equals working in the same field will go and want to review it. To see the step by step, they went through, many mathematicians around the world went through, many of them probably did not fully understand, but those who understood, reviewed, and here is the problem. Someone found an error, which is exactly Andrew Wiles' biggest fear, right? Somebody actually found a very fatal error that actually made a mistake somewhere. So the proof was not true.
So it's still unsolved.
Still unsolved. Well, as of 1993, right? So you're asking me the last part of the problem. I'll come there. It was unsolved as of June 1993.
That's all I want to know, though.
So he was probably devastated almost, but he's not a kind of, although he's a shy, he's a very determined person. He did not give up. Yes, Shri.
Is it the one solved more than 7?
Hang on. So he did not give up. He went back. He again went back to shell, right? And he actually, so while coming this, he used many different concepts to come to this, and he discarded some concept that, look, I want to use this instead of this, and at some point, now he retracted all the steps, all the way to the front, and he looked at different approaches again. And some of the concepts that they discarded, that it's not useful to solving it, he revisited them. And by 1995, he came up with one more attempt, using a different, and now he worked with another graduate student. Do you know what is a graduate student? Who is a graduate student? Yeah?
They already graduated? Or?
They're close. So it will be good for you guys to know. Once you finish high school, right, most people in this country go through what is known as an undergraduate program. It's a 4-year, most people go through undergraduate. There are other variations, but most students will go through a 4-year undergraduate program. Right? You might go to engineering, medicine, law, arts, whatever you like, but most students will go through 4-year it's called undergraduate program, it's also called bachelor's. Okay? After that, many people just go to the job and settle down. But a few of them will go to the next level called a graduate program, also called as master's program. You might have heard master's, right? It is usually 2 years, some may be 3, some may be 1, but usually 2 years. It's called a graduate program. So that's master's. Only few students will pursue that. After that, some more will pursue, and most will settle down after master's, but some of them will go to next level called PhD, or Doctors of Philosophy. Not exactly philosophy, but next level. They're very narrow, but very deep. Now they're getting into the cutting edge of unknown things they're trying to research. And some people even continue after that, they go to what is known as postdoctoral. They're going even after PhD. But graduate students are those who finish the undergraduate, but work with other professors, and sometimes even PhD students might be called graduate students. They work with professors to solve these problems, research studies. So he worked with he recruited a very smart graduate student called Richard Taylor, and they both worked together for the next 2 years. And in 1995, he came up with a revised proof. He published in one of the well-known journals, which put the last nail in the coffin of Fermat's last theorem. So he did prove this time, and a lot of peers reviewed, they agreed that it is a true correct proof. So Fermat's last theorem finally got proved in 1995, after 358 years after it was first written on the margins of Arithmetica by Fermat. Now, we call it Fermat's last theorem. We could have called it Diophantus theorem, right? Because Diophantus was probably the first one who proposed it. But it got popularized by Fermat's interesting story writing on the margins of the book. Okay? So, today, so many of you asked the question. Is the question answered?
So it's solved.
It got solved in 1995, about 19 years back.
Who solved it?
Hmm?
Who solved it?
So in India, we have an interesting story. I teach Ramayana. Everybody knows Ramayana?
Yes.
So tell the whole Ramayana, right? After listening to the whole Ramayana, someone asks, who is Sita? How is Sita related to Rama? If you know Ramayana, that will be an obvious one. If you don't know Ramayana, you don't understand the joke. But Andrew Wiles is the one who started, who solved it, right? So, to the other question, the Millennium Math problems, which we are going to talk about in the next year, and the next week.
Next year.
Next week.
Year.
Yeah, next week is like next year.
25th.
So, we're going to talk about what is known as Millennium Math problems, which were greatest unsolved math problems as on the year 2000. So this missed by 5 years because it got solved in 1995. We'll talk about that in the next week. And those problems, in the year 2000, an organization called Clay Mathematical Institute, a great mathematical institute actually based in Boston, in Massachusetts, in the United States. They worked with a lot of mathematicians around the world to identify the greatest unsolved mathematical problems as on 2000. And they found 7 of them. And they said these are the problems of this century. Because if you solve them, you're advancing math by a century. But it's huge. They're going to have huge implications for science and especially physics and for mathematics and other fields. So if you can solve any of them, any one of them, nobody can probably solve 2 of them, but even one of them, solving them is like you will instantly become one of the greatest mathematicians in the world. Now, but in addition, just to catch everybody's attention, they also announced a $1 million prize for each problem. So if you solve any one of them, you will get $1 million instantly. In addition to that, you will, so there is no Nobel Prize in mathematics. Mathematics has the Nobel Prize in physics, chemistry, etc. But there is an equivalent prize in mathematics called Fields Medal. Fields Medal is considered as like a Nobel Prize of mathematics. You will definitely get the Fields Medal if you solve any of them. But the most important of that, if you do this, I mean, your name will be etched in the history of mathematics forever. Okay? You will be on the front pages of newspapers, and everybody will come and want to interview with you if you solve any of these problems. However, to even understand some of these problems, it will probably take several years to even understand the problem. Unlike Fermat's last theorem, which is easy to understand actually, although it is hard to solve. Right? Some of these are much more abstract. So I'll try my best next week to give you a glimpse of what those problems are. Some of them are very abstract, you won't probably fully understand. But my goal is to hopefully give you a trigger like what Andrew Wiles got when he was 10 years old. Maybe you will not fully understand today. Maybe over the next few years you will just try to understand maybe one of them. Even if just one of them you try to understand. And maybe when 23 years or later, 30 years later, or 40 years later, you will spend enough time to prove it. Or maybe you will inspire someone else to solve it. Or maybe you will be part of the solution somehow. And then my goal is solved. And spending all this time to spend time with these guys, with you to teach this. Because Fermat's last theorem is a great story. Right? It's almost like a suspense thriller as we go from 2000 years until now. But there are many such mathematical stories. Who said math is not interesting? Somebody said, people, math is boring. Is this part boring? No. The math, if you don't take interest, if you just do addition, subtraction, multiplication, division, don't do anything else, it might sound boring. But math is full of fascinating, amazing stories like this. If only you dig a little bit deeper, right? And try to find the beauty of it. And that is the whole goal of this program, to show the beauty of that. And maybe the Andrew Wiles of the future is in this room. Who knows, right? So, any questions? Yes, Sri.
Never mind.
So, I'm going to give you a couple of projects for this week.
Oh, I got
Yes, right.
Was Andrew Wiles, when he was a child, you said that he was in the library, right? What book was he reading?
I'm not sure exactly what book, although if you Google research you might find. I don't know exactly what book, but some book that refer to this. And you might actually get inspiration from a different book. There are lots of books. If you are interested, maybe if you come to my house, I have hundreds, I know Sri sees that, I have hundreds of books. And hey, you still have that book, right?
Oh, yeah. I'll bring it next week.
Actually, I need it for this week. Maybe I'll collect it because we're going to talk about it next week.
Okay.
Right, it's the same one.
I feel like after someone would go to you.
After Sri, maybe after next week, you can take it. If you come to my house and you will see hundreds of books, maybe if you want to read one of them, and even get a glimpse of it, even if you fully don't understand, you might get an inspiration, you might get your Fermat's last theorem, right? Which, a few decades later, you might solve, right? And I'll be the happiest person if you do that. Even if you, okay, let's say Andrew Wiles in 1993, okay, when somebody found an error, and he probably was devastated, and he stopped there, and he was not able to prove it, let's say. Do you think everything that he did for the previous 7 years is a waste?
No.
Certainly not, because while trying to prove Fermat's last theorem, he proved many other things, because there is never a straight line to any challenging problem. You need to go through a lot of small diversions, and on the way, you might actually find something even better than your final goal, right? He actually found a lot of other mathematical principles which are helping math in other ways, apart from Fermat's last theorem. So even if he failed in his final goal, which is to prove Fermat's last theorem, his effort was not wasted. And that's a very important thing that you learn, right? In science or math or any field, when you try to do something challenging, there is no straight shot to it. You have to take a lot of other things, a lot of other directions. In fact, Newton, who is considered one of the greatest scientists and mathematicians, he said, I stand on the shoulders of other great people. And what he means by that is, whatever I tried to prove, whether the universal theory of gravity, which you'll probably learn in physics later, or the calculus, which he invented to prove the theory of gravity, it's not my own effort. I stood on the shoulders of other great people, means I actually learned from others and built on top of that. And I'm sure other people will extend my theory to others, just like Pythagoras' theorem got extended through all this, right? So I hope you will take one thing out of this class, just to take something that you like, that you love to do. Not just because you have got an exam for it, or when you grow up, you have a job for it, because you love to do it. Just like Fermat, his job was a judge. Nothing to do with mathematics, but he found a passion, right? And hopefully you will find something that you would love to do, even if there's no other reward, just because you love to do it. And if you do that with passion, you will find lot of rewards, right? That initially you might spend a lot of time trying to solve. When I started doing all this, it's how do I know all this, right? Nobody asked me to solve, learn all this, but for last 10, 20 years, I love to do it, I read it, and today I'm able to probably make a small difference, hopefully, to you in educating. So same thing, I hope you will take some of these and take it forward, okay? So, of the 7 problems, there's some great problems which are unsolved. Just like Fermat last time, there's one particular one which is now considered the greatest unsolved problem, and we'll spend more time about this next week. It's called Riemann hypothesis. We'll talk more about it next week. Today that's considered one of the greatest unsolved problems, and if it is solved, that will actually advance mathematics, and particularly what is known as cryptology, the study of secret codes, including passwords. Not simple passwords, but it's like if you go to NASA, if you go to military, there are a lot of important key passwords. And the people working on how to break passwords. And sometimes my son says, that's it. And every week he has a new passion. Sometimes 1 week his passion is, I want to become a cryptologist. Right? Because it's fun to break passwords. And his first goal is to break the passcode on my iPhone. But Riemann hypothesis is really at the edge of cryptology.
Has he done it yet?
He actually broke that one. But not by any mathematical things, but probably somehow stored it.
I did that so many times to my mom.
Huh?
I did that so many times to my mom.
You want to do that too?
No, I just want to be a soccer player whenever I grow up.
You want to become a soccer player? That's great. Maybe one day you'll play the FIFA World Cup. See, there you go.
I'll get a penalty shot and score.
But the important thing is whether you pursue math or science. Science, for example, is fascinating too, right? Many things which were considered impossible. I can guarantee you, what things which are considered impossible today, they will be solved during your lifetime. May not be our lifetime, maybe your lifetime, maybe a few years later. But things like, we talked about probably a few weeks back. What are some of the things which looks absurd or impossible today to solve or science? What would you like to do if you couldn't do anything? Anybody can think of teleportation? It does appear here and appear in India, at your grandmom's house, instantaneously.
We're probably going to use tubes to do that.
What is that?
Tubes that go underground. Something.
Underground?
That would take
But how many
forever.
tubes? You have tubes everywhere? From everywhere?
Yeah, yeah, probably.
But actually, interestingly, scientists today do it already at an atomic level, where a particular atom or a particular particle can instantly disappear from one place and appear somewhere else. At an atomic level, right? What are we made of? Atoms. So if you can somehow figure out, we haven't figured that out at any, what you call a macroscopic object, like things that you can see. It is only possible today at microscopic or atomic level objects, right? But if somehow, someday, somebody can figure out, this is made of atoms. If you can somehow figure out the entire replica of all the atoms, right? It disappears here, appears in your hand. That is teleportation. Or maybe one day, we are made of atoms too. The whole set of atoms disappear and appear at another place. Or invisibility. Today invisibility is impossible, right? But how do you know? I was talking about it a few weeks back, I don't know, to your class or a different class. About just 150 years back, okay? Many of the greatest scientists at the time felt that it was impossible to fly, for a human being to fly, to find an object, right? Not the birds and other things, but actually a man-made thing to fly. They were proved wrong within a few decades. So, and it's not by somebody, it's by some of the greatest scientists at that time. So, don't take anything as impossible. Some of the problems that we're going to discuss next week, they're probably impossible, considered impossible by most people. Otherwise they wouldn't be there, right? But I'm sure somebody will solve. Yes?
I don't think like the teleportation should be done by atoms because they could be misplaced. Your head might be down there and your foot might be up here.
I'm sure people, if you try to do that, that will happen on the way. But maybe you can come up with a technique to replicate exact thing someday. Maybe not. Let's not start with the original. Let's start with this thing, the eraser. Okay? Less risky to if you misplace this and to this and, right? If you misplace, hey,
Can't we
that's a
use
little bit more
an
risky.
ant?
Huh?
Why can't we use an ant?
A?
An ant.
But ant is still alive, right? You're still risking their life. Maybe no, it's less risky with this. Yes.
But how about if like you could like kind of like arrange the atoms like one way here and then like so like by atom you can like make it in another place because they can already do it here like.
Great idea. Why don't you try? Right? So, no, all those are great. My idea is not to solve teleportation right now. Right? If I can solve it, I won't be here. Right? But, so don't give up something just because it is considered as impossible. It could be science, it could be math. Right? There's $1 million math problems. Maybe you just want to do it because you want to get $1 million. But trust me, if you reach there, that would be cool, right?
Yeah.
But I'll tell you one thing. One of the 7 problems is already solved. We'll talk about it next week. But here is the interesting thing. The person who solved refused to take the $1 million.
What?
Yep.
You
You know why? Well, if you really solve the problem, $1 million probably is the least of your concerns if you solve it, right? Because to solve there are many hard years to do that. And money probably doesn't make any more difference to you at that stage. Because you're immortal. You know what is immortal? When we are long gone back, we remember about Diophantus and Pythagoras and Ramanujan and Aryabhata, but we don't remember about billions of other people who lived. Why? Because they made a difference. They did something that kind of took the humanity a little forward, right? In solving something. If you solve any of these problems, that's exactly what will happen, right? Your name will become immortal, will be remembered for the next hundreds or thousands of years. $1 million, you can blow it away, right? Maybe not blow it away, maybe you have a good life. And have $1 million, I want you to have $1 million, right? But it is a much better way to have $1 million than winning a lottery ticket, right? But I will also tell you, this is probably the hardest way to make $1 million, okay? But it is worthier than any other $1 million, right?
Not really. You could discover a new medicine.
That's a good way to do it too, right? That probably will help people even more, right? So there are many challenges that you can solve, but have some challenge because you love to do it. It could be science, it could be math, it could be you want to write you want to compose a great musical song or just a song, compose a song that's so great that people will remember. Like Shakespeare's books, people still read. Not everybody's books everybody reads, right? Maybe that's your dream, pursue that. Nothing wrong with that. But maybe you want to become a Pele of soccer, right? Pele of United States. Anybody knows who's Pele? You must be knowing because if you like, okay, who is Pele?
He was a soccer player.
He was a great soccer player. Which country is from?
I
think he's from Brazil, right? Why do you talk only Pele? There's so many soccer players, thousands.
He's probably one of the greatest still alive.
Right. So whatever you do, try to be the best. It doesn't matter what it is. But do it because you love to do it. Okay? If there are no questions, I'm going to hand you out these handouts, and there are 2 interesting projects. I want you to spend enough time with these projects. Okay, read through this so that you kind of refreshes everything that we talked about, but you also do the projects. And one of the projects is, let me give this to first. Okay. If you go to the last page, the first project, look at this. Actually, there is an equation here. Somebody says that 3,987 raised to the power of 12 plus 4,365 raised to the power of 12 is equal to 4,472 to the power of 12. Now, if that is true, everything that we talked about now is false. Right? Because that's what we all proved, that it is impossible to find x power n plus y power n equal to z power n. But this one just proved.
Uncle?
Yes?
But is there a possible way that, oh no.
Okay. So do some research about this. And the second one, I want you to write.
I love using calculators.
You are allowed to use calculator for this one. Because otherwise you will take a long time. It will take the whole week to do the math. And you can
Someone came to the class and actually solved the problem. What if someone actually solved the problem?
Great. And you're allowed to take your parents' help to do this because it's hard one. The second one is another fascinating story. I'm not going to tell you the story. I want you to find the story yourself. It is a story related to what was a very unremarkable number called 1729. I want you to do some research and find out what is the story behind it. Okay? Do your own research. Write as much. Don't just write 2 sentences. Okay? Find out the full story behind it. Just like make it as interesting like a suspense.
You want us to write the entire story?
Yep. Absolutely.
Oh,
Absolutely. If you want to take 6 pages to do it, I'm fine with that. Okay? Yeah, you're allowed to type. You can either write or type. You can type and take a printout, I'm fine with that. But I want you to take enough time to find, it's a very interesting story. It's as interesting as this. And it's one of my favorite personal stories, favorite mathematical stories. And I hope you will find it and you will write it too. Okay? Yes?
Was Andrew Wiles' theory so simple that I could solve it?
Maybe find out. These are public information now. The best thing about math and science or any of these fields, once it is proved, right, it is publicly available. You can Google it and you can find it. But it will probably take several years to understand.
I was hoping that if at the end he didn't solve it, I could solve it.
No, why take a problem that is already solved? You have $1 million problems that are not solved yet. There's 6 of them. Take any one of them. And if you solve that, you will be the next Andrew Wiles.
Why can't we get all Bill Gates' money?
If you do the same thing that Bill Gates did, see, here's the thing about money, right? All of us like money, right? All of us like money. And I want you to have a lot of money. But there are 2 ways to make money. One way is keep buying lottery tickets. Okay? And probably you may or may not make it. But even if you win, right? Compare that with the Clay Mathematical Institute. You solve $1 million math problem. Let's say you can win $1 million by winning the lottery or solving one of the unsolved math problems, millennium math problems. It's much harder to do the second one, the math problem, but much more work, because apart from the money, what else you have? Solve it. Yes? Good?
There's actually 3 ways to make money.
Okay.
The third one is terrorizing people.
Terrorizing. Okay, which one is worthier of the 3? You have some very creepy ideas.
What does Bill Gates do?
What did Bill
He's
Gates
the
do?
owner of Microsoft.
But no, she didn't ask what is he, who is he? She asked what did he do?
He made money because he was the owner of Microsoft.
I know you like the money, but here's the thing about money. Okay? If you do something, when he started, Bill Gates started what he calls as Microsoft today, right? He probably had no idea that he will be the richest billionaire in the world, right?
Not yet. 80 billion is the highest so far.
Right, but the point is, when he started Microsoft, he probably had no idea about it, right? He started something because he loved it. He loved to do the coding. He actually, and then he went around and followed. He dropped out of Harvard to do that. How many people will do that? And you can drop out of Harvard just because it's too tough for you. But he found a passion, right? He found something and he spent his lifetime doing it. And here is it. If you do find any one thing that you love to do, and you do it, even if there is no money in it. Okay? This is the interesting thing about money. If you do it because, even if there is no money, because you love to do it, and you spend your passion, time, energy in doing it, money will follow. You will get money. That's what happened to Bill Gates. He followed it so, and same with Steve Jobs, any successful person, right? When he did it, well, everybody likes money. Who doesn't like money, right? But if money is the only thing that you care about, probably you won't get it. If that is the only thing. And even if you get it, you just get money and nothing else. But Bill Gates will be remembered for hundreds of years, sure. Even, I don't know about thousands, but he will remember for a long, long time. Not just because he became the richest person at some time, but because he made a difference to the computer world. He made a difference to everybody. His vision was, it probably not the only one, there are a few other people, to have every person in the world have their own personal computer. That made a difference, right? Computers made such a huge difference. Have something that burns like that. And if you do that, money will automatically come, right? Then you will have everything that you want. Don't just focus on money. Focus on something that you love to do it. And it is not necessarily what Bill Gates did. It's whatever you want to do, and the money will come. Yes, Sri.
You remember how you asked us that if you win a lottery ticket, and what's the difference of winning the thingy, the $1 million from that?
Yeah.
You can get satisfaction, respect, and fame.
Great. So you get a satisfaction, respect, and fame, and money as well, right? Money. That's a byproduct. See, the best money that is earned is a byproduct. What I mean by that is you want to do something and you respect it by everybody else because you made a contribution, and money automatically comes. In fact, you will make a lot more money than $1 million. I promise you, if you solve any of these problems, right? The best companies in the world probably want to hire you. The best universities in the world probably want to hire you, right? And you will get a lot more money if you solve this. But $1 million is probably a good side benefit, right? Not bad. Not too bad.
You get fame if you are a terrorizer because you would be known as the real
But you want the satisfaction.
Yeah, you
Well,
Maybe she will. That's her goal.
We won't get respect, except from other
You won't get respect, that's for sure. Right? There are two kinds of fame. Famous and infamous. You know the difference? They both are famous, except that is a bad famous. You want a good fame or a bad fame?
Oh, I never said I wanted to be a terrorizer.
I don't mean you. I don't take it personally. Anyone, right? Which fame would anyone want? A good fame or a bad fame?
Good.
Good fame.
Not everybody.
Not everyone. Okay. Then I'm sure that's why there's some such things
would
will
want
happen,
that
right?
fame.
All right. Any other questions?
No.
If not, have a great week and spend enough time. Hopefully do some research on both projects, and we'll meet next week.
Bye-bye.
Bye.